This chapter, as you can see from the front cover there, is all about work. Work and energy, and naturally we have a very specific and probably different from normal usage definition of what work is. So we're going to start out with a fairly basic and direct one. Work is the product of force and displacement. Okay, so formula wise, we say work is capital W, force, and displacement. But there's an issue here based on what we know already, because both of these are vectors. And you don't, I don't think you've seen this in math, you don't know how to multiply vectors together. So let's take a couple examples and then we'll come back and revisit this. But keep that in mind. So let's take a simple example. We're going to have a box here. We're going to apply a force to it of 50 newtons. And we're going to move it from here to there, which is 10 meters in distance. Well, in this case, our force is being applied to this box in order to move it. And that's the very definition of what this work is. So it's the product of force and displacement, or another way of looking at that is the product of the force that causes the displacement. So in this case, all we have to do is say, okay, well, I'm going to multiply my force, 50 newtons, times my displacement of 10 meters. I get a result of 500. Sometimes you'll see this as Newton meters, but we actually have a different made up unit for it called joules. So a joule is equal to a Newton meter, and this is Joule. It's named after a physicist who did a lot of early work looking at energy and how things are moving. It is not joule, it's joule, like jowl, but with an E. Very, very easy. However, what happens if instead of just tugging it along, we now apply our force like we tie a rope on a sled? Let's say that we apply it at 45 degrees, still 50 newtons. We'll still move this thing 10 meters. But now, not all of our force is actually going into moving it that 10 meters. Here's what we have to look at. How much of my force is actually, if my displacement is in that direction, how much of my force is actually applied in that way? So what we want to do is find the component of force that's parallel to this. I'll call it Fx. How would we go about finding that? Trig. You got it. Which side of if this is, I'll move this up here so it's a little more obvious. That's a 45-degree angle. Which side of our triangle is this? The adjacent side, which means it's related to the hypotenuse by cosine. Yes. So this would end up being, and doing just a little bit of rearranging, our 50 newtons times the cosine of our angle, 45 45 degrees. I know what the cosine is, I don't know what that product is. And that's the amount of force that actually goes into this work, which we could rewrite as saying the total force times the displacement times the cosine of that angle between them. Okay, so that would be 50 newtons times 10 meters times the cosine of 45 degrees. Somebody got me? Ben?
35.
35.36, so 35 joules. So that's really the only trick with work. We have to figure out how much of that force is actually going parallel to our displacement, and that's where this handy cosine comes in. Now, revisiting what I had said up above about we have to multiply these two vectors, this is one option. So work is equal to the force times the displacement. There are two options that you'll learn as you go through math of how to multiply vectors together. The one that we're going to do is notice that there's no arrow above work. That means work is actually a scalar value. When we do a certain amount of work, 35 joules, it doesn't have a direction at all associated with it, but force and displacement do. So we need a method to take these two vectors and kind of convert their product into a scalar, and that's what we did up here. When we look at just the things that are parallel, we call this a dot or scalar product. And what results is a scalar. There is also a vector product, which is called a cross product, and I don't think we're covering that at all this entire year. But it's another way to multiply two vectors that are perpendicular. Well, as it turns out, if we want just the component of the force that is parallel to the displacement, we already figured out how to do that using trig. And that's how this dot product works out too. So the more general form is the force times now the distance that it's moved times the cosine of the angle between the force and the distance. This is an important work formula. Yes?
Can force and displacement have different directions?
You bet. We're going to do a couple of examples to see how that would happen, or what that would mean. And we're going to apply this and see how it's pretty simple when you sketch it out to get this. So let's take our box again. We already saw if we're going to assume that the box is moving this way, and we'll keep it simple, so we'll make it 10 meters again. But now, let's see what would happen in different directions. We saw that if we pull it straight, well, let's take that for a moment. If we say F1 is in this direction, say, how can we write this? The theta, which is the angle between F1 and D. What would theta equal in this case? 0. Going the same direction, right? What's the cosine of 0?
What is that? I'm sorry. What is that symbol between the F and the D?
That's supposed to be an angle. I forget how to do that. Is that an angle? That's the angle symbol for angle between, isn't it? Or is it the other way around?
It's the other way.
Okay. I liked math, but I'm not really a math guy, so I forget some of the exact way to write that. But I mean the angle between that's 0. What's the cosine of 0? 1. So we just get the force times the distance, which is what we saw in our first problem. If we took a force 2 45 degrees out, then theta 2 which is the angle between F2 and D. That's 45. So we saw that it did a little over half of the work. Something like that. Now, what if we took, and we still have our object moving this way, what if we took force 3 that is at a right angle here? What's the angle between our force 3 pulling straight up and our box moving that way? 90 degrees. What's the cosine of 90? 0. So that means actually this force does no work. It does not contribute to this motion at all. Keep going. Let's take force 4. What's the angle between our force 4 and our displacement? I heard some people mumble, I think it was 180. Let's do that one. Let's say the work applied by 4. Okay, that's equal to the force, we'll call it, for simplicity, we'll call it 50 newtons. I'll just write it out, cosine of theta 4. Now let's put in values. We have 50 newtons. Our displacement is still 10 meters that way, times the cosine of 180. What is the cosine of 180 degrees? -1. So -1 times 10 times 50 is -500 joules. So this is actually doing negative work. It's doing work against the motion. Can anyone think of any possible physical situation where this would be? That you'd have motion in one direction, force in another.
You're trying to push something and someone's pushing against you?
Okay, so if two of us are pushing on this, I might be pushing that way, but it's still moving behind me. That's a good one. Friction is a good one. That always works like this. Friction's always doing negative work. Mm-hmm.
If it's already moving and not fully decelerated yet, if you're pushing the opposite direction in the movement.
So if you stand out in front of a car, a la Superman, try this at home, and try and stop the car, then you would be doing negative work on it. A second way to think about this. So there are two ways that I want you to think about what work is. One, it's the product of force through a distance, and that's where we get that formula from. Another one that we'll work with a lot is that work is the act of adding or removing energy from an object. Or maybe I should say, is how much energy is added or removed. And that's a really useful one to keep in mind as well. Now you might say, well, fine. What is energy? And that would be a very good question. Because we all have probably kind of a concept of what energy is, but as far as a definition goes, I'm going to rely on Richard Feynman. This is a part of his collection of lectures that he gave when he was teaching at Caltech, California Institute of Technology. And he said It's important to realize that in physics today, and now this was maybe 50 years ago, but it's still true, we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It's not that way. However, there are formulas for calculating some numerical quantity, and when we add it all together, it gives 28. That's in quotes, just a random number. Always the same number. It's an abstract thing in that it does not tell us the mechanism or the reasons for the various formulas. So this whole chapter, we're going to be relating work, which is kind of adding or removing energy from things. We're going to be learning different ways to calculate energy and their relationships and how they can go from one form to another. But keep in mind that we don't really have a definition of what energy is. It's some characteristic. We're going to learn several different ways of measuring it, useful things to do with it. But that's kind of what it is. It's sort of a tool, almost, that we're going to use. And here is one way to measure adding or removing energy from something. So if you are pushing on something, you're adding it. If friction is acting on something, it's kind of taking energy away from that object. The last thing yes? Go ahead, Marcus.
Sorry, this might be a little off topic, but how does heat energy, is that able to transfer to anything but heat energy?
Yes, lots of ways. In fact, it's really importantly, we use heat energy to make automobiles go and to make power plants work. In fact, almost all of our energy is generated with heat as sort of an intermediary. So when you heat something up, what happens to the atoms and molecules that make that thing up? They get farther apart and they accelerate, they go faster. Heat or thermal energy is a measurement of how fast those things are moving, bouncing off each other. Well, in the case of most energy production, we use something to heat up water. Then that water expands because all of its molecules are going faster and they want to spread out. And that allows us to, if we put something in between that they have to push past, we can use that to translate it into mechanical, and then if we want to, electrical energy. So we actually do that all the time. The trouble is that that's never 100% efficient process. So we lose energy, and it's not like the energy is just gone. It's just not energy we can recover and use usefully, have a useful purpose for. It just goes out. That's probably the most basic law of nature that we have found, is that free energy that we can't recapture, it's called entropy, is always increasing in the universe. And it will always increase. We can take we can draw a box and we can reduce that free energy in there and capture it, but in doing so we actually increase outside the box, so that as a net we're always going, that entropy is always increasing. Is that the first law of thermodynamics? I'm not sure. It's one of the laws of thermodynamics. Well, sort of, but chaos theory actually deals with how you can find order from things that appear chaotic. Let's talk about one more thing. We've talked about constant forces that are pretty standard, and that's what we'll do a lot of our calculations on. You apply 10 newtons in this way, you apply 20 newtons in this way. But let's consider instead what happens if we have something that, let's start with a simple one that is still constant, but that will expand that. Let's say that we have a force here and a displacement, and we're charting this. And we say we apply our constant force for now. Like so. And so this is at some force, I'll just call it F, F1, say, and it's for some distance, E1. Now we know that we can find the amount of work if we say take the force times the distance. This graph is sort of assuming that they're in the same direction already, that we've already taken any part of that force that isn't in the direction of the distance, and we've already taken that out. So we could find the work here. What does that tell us about the graph, though? How does that relate geometrically to our graph?
The area equals the work.
That's the area underneath our graph. So work is also another way to find it. If we've got a varying force, especially this is useful. If we've got a constant force like this, well, it's easy just to multiply. But if we have a varying force, we can do this. So work is also the area under a force versus displacement graph. While you guys get that, I'm going to set up a little different one. Okay, so still fairly simple and straightforward. Let's look at these different areas of this graph. So now we've got a varying force. It actually even changes its direction. So an object is continuing to move in one direction. For the first 3 meters, you're actually applying a negative force, so you're pulling back on it. And then at the 3 meter mark, you start pushing. Your force is decreasing until it gets to 0 force at 3 meters, and then starts increasing in the opposite direction. So this is actually, let's see, how could we do this? We could consider this like your car is moving forward, and you hit the brakes really, really hard, but then ease up on the brakes as you start to slow. And then you hit the accelerator, and you continue to hit it, and you continue to push it down. So like you slow for a kid until you recognize them. And then once you do, you start speeding up. Oh, I said too much. So let's look at portion 1 and then portion 2. The work for portion 1. How would we figure out the work for portion 1? Could be cosine, but here's the problem. That first formula that we had, it only allows us to have a constant force. So this force is applied parallel to the displacement, but it's not a constant.
Would you just do a negative 10 times 3 times 1/2?
Which you got to how?
Area of the triangle.
Area of the triangle, which we know is 1/2 times base times height, which would be 1/2. The base of this is 3 meters long. The height of it is negative 10 newtons. So assuming 2 significant digits for each of these, we'd have negative 15 joules. Section 2, it's set up the same way, except, so it's still a triangle, 1/2 base times height. The base is still from 6 to 3 meters is still 3 to 6 meters is still 3 meters. But now the height of this is 10 newtons. So we'd have a positive 15 joules. So at first, when we were braking, we were taking energy away from it. So the energy of the car went negative, or our force did negative work on it. when we started accelerating, we were essentially adding energy to the car. So we did positive work. How much total work did we end up doing? 0. Adding those up tells us the total work. So essentially, from the very beginning to the very end, we didn't add or remove energy from the car. We kept it steady. Now, in between, it did do some stuff. And other energy was converted, but that's for another day. Okay? So we've got a little over 15 minutes to work. I might be persuaded to extend this, but let's see how much we can get through because it's actually pretty quick. Homework 4.1 is on work. I'd ask that you try your best to finish. It's two-sided. Try your best to finish for tomorrow because all of it's pretty simple stuff like this, and once you get it, it goes very, very quickly. I know that it won't come immediately to everyone, but we will do our best. Yes.